Hello and welcome to this presentation of the Eagle Scout Kit Assembly Senior Project. A quick introduction to Senior Project Team 1. We had Tyler Hayes, Alexander Sicoli, Andrew Manduzzi, Tyler Swenson, and Manny Rodriguez, along with myself, Kyle Wiggins. We came from a variety of different backgrounds as far as both our majors and our co-op experiences, including several of us who had experience with automation that came into good use during this project. The problem presented to us by our sponsor Terryberry was to find a way to improve on their current manual process for assembling Eagle Scout medals and packing them out into award kits that are presented to Boy Scouts upon attaining the rank of Eagle Scout. Due to the relatively low production quantity of these kits every year, they do not have full-time personnel dedicated to working on this process. Instead, their operators work on it as kind of a side role to their primary responsibilities. As such, they are inexperienced with many of the steps involved, and many of them consider the process to be somewhat time-consuming and tedious. Based on feedback we received from Terryberry in the initial stages of the project and a study of their current process that our team collaborated with them on, it was determined that the most problematic step in the process was the ribbon pinning step. In this step, the top bar, which you can see in the image on the upper right of this slide, is pinned through the ribbon that you can see in the image below it. This is a fairly troublesome step to do by hand, and operators would often either inaccurately place the ribbon or the top bar into the ribbon, or they would prick their fingers in the process of doing this. As such, we decided to develop an automated machine to improve the efficiency of this process. The goal for this machine was to enable any operator in Terryberry's facility to match the cycle time for the ribbon pinning step of the process to that of a skilled operator performing the same process. In order for a ribbon to be considered properly assembled, it must be pinned to the top bar such that the ribbon does not show above or beyond either side of the top bar, as you can see in the image to the right. In addition, in order for any automated solution to be viable to Terryberry as a cost-effective solution, it would have to have a relatively short return on investment. Our design was required to have a means of visually indicating the current production condition to the operator. This could be a stack light, a human-machine interface, or any other means that we felt was best suited for the application. In addition, the machine was required to have an emergency stop button and any other features that we felt were required to ensure the safety of the operator. Terryberry set aside a 12-foot by 12-foot floor space within their facility for us to install our machine into, which provided our footprint constraint for the machine. Air and power drops were defined during the initial phase of the project as well. In order for our machine to be considered successful by Terryberry, the assembly processes that the machine performed would have to have a failure rate of 2% or less during the final runoff testing that was intended to be completed at Terryberry's facility once the machine had been built. The first challenge our team had to overcome in this project was to determine which steps of Terryberry's current process could be improved through automation. In this, we not only had to consider technical challenges related to some of the steps, but also the cost effectiveness for Terryberry to implement these solutions. In order to achieve this, we completed a study of their current assembly process and came up with proposed solutions using automation to several steps of the process. We then used the estimated cost and estimated reduction in cycle time for each of these solutions to conduct a cost-benefit analysis. Once it was determined that we would focus on the ribbon pinning step of the process, we needed a way to secure the flexible cloth ribbon during the pinning process. Several different methods of doing this were brainstormed during the design phase of the project and then prototypes. Of the physical prototypes made, one of them worked particularly well, and it was decided that that method would be implemented into our design. This will be discussed later on in the presentation during a more technical walkthrough of our design. Finally, we had a cycle time requirement of 15 seconds per ribbon the top bar assembly in order to match their experienced operator at this step of the assembly. We achieved this by developing a 6-up fixture for both the ribbons and the top bars, and then using a pneumatic cylinder to press the top bars into the ribbons. I'll now hand this presentation over to Alexander Sicoli, and he will talk about the mechanical design of the machine.
Thanks, Kyle. So looking at the mechanical design a little deeper, we wanted to come up with a streamlined process so that any operator could step in and work this assembly line as efficiently as possible. So what we did is we came up with a workbench style design so that the entire assembly process of the ribbon takes place on just this workbench. So on the left hand portion of the machine we see the pinning operation occurring, and that's where the operator will load in the ribbon and the top bar, and that will get pinned together and the backings will be put on. After the operator completes that operation, everything moves over to the right hand side where the operator will finish installing the extra rope and eagle charm to complete the operation of the pin design. So all the components are nicely sorted in the bins above, so each operator knows exactly what components go in on their portion of the workstation, and we wanted to design the machine overall to improve the safety, ergonomics, and efficiency of the ribbon assembly process. So looking a little closer into the fixture design, this was one of the most challenging parts of this machine, as we said previously in the challenges, was creating a fixture that can handle a flexible ribbon. So what we came up with was a 2-pin design that will grip the ribbon, and then a clamp that will secure the ribbon in place for the pinning operation. So the way we accomplished this was the operator grabs the vertical handle and pushes that U assembly backwards, which opens up the pins in the hole, and the operator installs the top bar first into a fixture down below on a platen, and then after that the ribbon is slid into that channel, and then the handle is released, releasing the pins back into place, constraining the ribbon. So then the operator pulls that tight and clamps it down. After that's accomplished, the operator hits the 2-hand touch and the pinning operation takes place, and then once that is done, the clamp can be removed and the pins are exposed to load the backing and the locking bells onto the ribbon and top bar assembly. So this whole process is, greatly streamlines it and makes it much easier and efficient for the operator. Instead of doing the whole operation by hand, they have a nice machine press to complete the pressing operation, which greatly saves on ergonomics. We tried to make as many standard parts as possible, so the pins are actually a standard purchase part, so it's not a custom made design, so if those pins get bent during the operation, it's really easy and cheap to swap them out. Overall, this fixture was created so that it would create a full package worth of ribbons. So that's where we came up with the 6 ribbons, and once the operator loads all of the top bars and ribbons into each one and completes the pinning operation, they'll have a full case completed. So that will greatly increase the efficiency of our process. Now the platen down below can be seen here. This is where the top bar is loaded into the machine, and this is what this whole platen will raise up and press the top bar into the ribbon, creating the pinning operation. So each one of these fixtures is floating on the subplate, and it's held in by an oversized hole with an oversized washer, and then shim blocks are placed in to precision locate each fixture in the XY direction. This allows the operator to adjust each fixture individually to make sure it lines up perfectly with the ribbon above for each case, so that we don't have any error and we're within the tolerances needed to properly install the top bar to the ribbon. So because this is such a precision operation, we wanted to make sure that deflections due to the pressure of the cylinder creating the pinning operation didn't create a too big of a deflection, causing us to be off in our direct dimensions. So what we did is we ran an FEA simulation simulating the force, the max force of the cylinder pressing up onto the block, and based on that is how we developed our stiffeners on the bottom, and that created a deflection of 0.007, which we found that this is well within our tolerance to maintain a good ribbon place or good top bar placement on the ribbon every single time. And once that good placement is found, the shim blocks are placed in the XY coordinates to properly align it, and then it is locked down with a bolt through the holes you can see. So then once it's set, you can forget about it. If it ever comes out of adjustment, you can undo that screw and change the shim blocks inside of there to realign it properly. So overall, we figured this is a very robust design that should keep producing accurate ribbon placements for a long time. Looking at the pneumatics, this was a very simple machine. So we just have a very simple circuit with a single solenoid for easy maintenance and simplicity. And we made sure it ran off of shop air pressure, so it's easy to hook up. And we also looked at how much force we would need for that cylinder. So we saw that we would have 60-pound platen with 10 pounds of force per ribbon times 6 ribbons. And then based on that, we worked with a distributor of cylinders and our own hand calculations to come up with a 2.5-inch bore cylinder with a 1.5-inch rod running at about 38 psi based on what we would regulate the shop air pressure down. And that should give us plenty of force with a good factor of safety to complete our pinning operation.
To control the cylinder, the team decided to use an Allen Bradley Micrologics 820 PLC. We have very few inputs and outputs needed to and from the PLC, so the low cost of the 820 made it an appealing option for us. An emergency stop button is included that will stop the cylinder from actuating whenever it is pressed. We have also included a 2-hand tie down that the operator must hold down on during cylinder actuation. This prevents the operator from sticking their hand into the cylinder well while the cylinder is in motion, where it could potentially get caught by the top bar platen. A cycle start push button is included that will light up at various points in the process for the operator to press. This is primarily used for fault resets and in between steps of the process to put the cylinder into to put the controller into a state for the cylinder to cycle. A multicolored dome light is used for enunciating machine status to the operator. Our team considered the idea of using a panel view HMI for this role, but we decided that there was fairly little information we would actually convey using it, and that a full-blown HMI would be overkill. Instead, flashing or solid lights of various colors from the dome light will be used to indicate various status states such as ready to run, cylinder actuating, or different fault conditions. The cylinder can detect 3 different fault conditions. Either the e-stop has been pressed, in which case the operator will have to release the e-stop and cycle the cycle start push button. The cylinder not being retracted at machine start, in which case the operator will be required to home the cylinder and then start the machine. Or a cylinder actuation fault, which can be triggered by an excessively long actuation of the cylinder. This allows us to detect either if the extended or retracted prox sensors on the cylinder are faulty, or if the cylinder itself is faulty. Further diagnosis of this is incumbent on the operator. Unfortunately, due to the COVID-19 pandemic, the decision was made to cancel the build phase of this project. Instead, the deliverables for this project were limited to the documentation of the ribbon pinning machine and the controls logic for the Micrologics 820 PLC. Our team was highly confident that the machine we proposed to Terryberry would be a viable solution to their issues with the ribbon pinning process. The greatest technical challenge our team identified during the design phase was going to be securing the cloth ribbon during the pinning process due to its flexibility. However, the success of our prototype of the pin method relieved these concerns going into the design phase. After the completion of the final design review, all parties involved were confident that the machine would work, and everyone was excited to see how well it would work once it had been built prior to COVID causing the cancellation of the build phase. There are several people the team would like to thank for their contributions to us completing this project. The first is our primary faculty advisor from Grand Valley, Professor Terry Stevens. He guided us through this project and gave us invaluable insight on the controls side of the project. We also have our secondary faculty advisors from Grand Valley, Dr. Sung-Hwan Ju and Professor Madina Ruzi, who provided additional insight during the design phase of the project to us. Last but not least, we have our sponsor contacts from Terryberry, Dan Young, Tad Evans, and Doug Kutchuk. They were immensely helpful in answering questions and were nice enough to invite us several times out to their facility so that we could gather as much information as we could in order for us to design the best solution possible for them.